Let's take a look at review problem 3.2, finding the solution of y double prime plus 100x squared y equals 0 as a series about x equals 0. So to get started, y double prime plus 100x squared y equals 0. And we'll start this as a power series solution about x equals 0. A sub n, x to the n. That's really x minus 0 to the n, but I'll suppress the x minus 0. Okay, now the first part is 100x squared y, so let's just multiply the thing by 100x squared times 100x squared. So summation n equals 0 to infinity of 100 a sub n x to the n plus 2, multiplying by 100 and also x squared. And then let's shift the index so that I have x to the n here and not x to the n plus 2. To shift the index, I'll start on n equals 2, 100 a sub n minus 2. A quick double check to see if this actually worked. If I plug in 0, I get a sub 0 x squared. If I plug in n equals 2, I get a sub 2 minus 2 is 0, a sub 0 x squared, x to the 2. So it checks. Next, I need y double prime, so I'll take two derivatives of what I see here. That's going to be summation n equals 0 to infinity of n times n minus 1 a sub n x to the n minus 2, bringing down powers here when I take two derivatives. And now I'll employ the standard tricks that if n is equal to 0 or 1, then this disappears. So I get n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2. Then I'll shift this series so that I have x to the n here and not x to the n minus 2. And that'll give me n plus 2, n plus 1, a sub n plus 2. Okay, so adding these two series up, we get that y double prime plus 100 x squared y is equal to summation n equals 0 to infinity of n plus 2, n plus 1, a sub n plus 2, x to the n, plus summation n equals 2 to infinity, 100 a sub n minus 2, x to the n. And I've almost got this lined up to add up, except that these start at different places. So let's make them start at the same place. N equals 2, n plus 2, n plus 1, a sub n plus 2, x to the n, plus summation n equals 2 to infinity, 100 a sub n minus 2, x to the n. Now, of course, I left off the first two terms on this first series by starting the first series on 2 instead of 0. So I got to throw in 0. So if I put in 0, I get 2 times 1 times a sub 2 times x to the 0 plus 3 times 2 times a sub 3 times x to the first. And that is supposed to be equal to 0. So the only way this happens is if a sub 2 is equal to 0. Also, 6a3 has to be equal to 0. And then also this thing has to be equal to 0. So that means that if combine the x to the n's, that means that n plus 2 times n plus 1 a sub n plus 2 plus 100 a sub n minus 2, that has to be equal to 0 as well. And solving for the higher index, that gives me that a sub n plus 2 is equal to negative 100 a sub n minus 2 over n plus 2 times n plus 1. Now I'm legally permitted to leave it like that, but it's a little bit easier if I write this in such a way that it's a sub n equals something. So everywhere I see an n, I'm going to replace by n minus 2 to get this. So here I have 100. I replace n by n minus 2 for n minus 4. This n minus 2, n gets replaced by n minus 2, so for n minus 2 plus 1 becomes n minus 1. And so that is my recurrence relationship for the coefficients. To implement this in Excel, so here's column A, here's column B, row 1, row 2, row 3, row 4, row 5, and so on. Okay, so let's put the indexes for the n's here. So I'll put 0 here and then add 1 to that and then carry down. So that becomes 1, 2, 3, 4, 5, and so on. Okay, now a sub 0 goes here, a sub 1 goes there. A sub 2, we just got done saying was equal to 0. A sub 3, we also got done with saying is equal to 0. Then for this term, that's going to be equal to negative 100 times a sub n minus 4, so I go back 4 steps to b1, and then divide by n, which is this number here at a5, times n minus 1, which is the number here, 1 above at a4. And then if I fill that down, that will give me, in fairly quick order, the coefficients in the expansion, the first few coefficients in the expansion. So that's how this can be programmed with Excel. Now this can be programmed with C++ or Java or Python, but that's how I would do this in Excel.